Okay, let's start with problem A. So given an array of length and tell us whether it is a non-empty, whether it has a non-empty subsequence such that the product of its element is not a perfect square. P can be obtained from A by deleting some elements. It is not a perfect square. Okay, so if either of them is not a perfect square, then I can take that element, right? Non-empty subsequence. Yeah. So if there is even a single element that is not a perfect square, then I can do that, right? Yeah. Okay, so if it is possible, then I print yes. Tell us whether it has a non-empty subsequence such that the product of its element is not a perfect square. Okay. So this gives me a yes right here, but it should be giving me a no. Okay, so if perfect. Oh, okay, this should have been the other way around. Okay, let's try to submit this. I hope I'm submitting the right value. Okay, great. So it has passed on the pre-tests. Moving on to problem B. So there are not many problems today. Yeah. First words were and zero sum big. So we decided to solve the following problem given two integers and int k. Count the number of arrays of length n such that all its elements are integers between 0 to 2 to the power k minus 1. The bitwise AND of all its elements is 0. Okay, so there should be at least one of the bits that is not set in all of these numbers. The sum of its elements is as large as possible. Okay. Number of arrays of length n. Okay, so the array's length should be n, and the sum should be greatest. So for the first n minus 1 numbers, I can take 2 to the power k minus 1 itself, right? And for the last number, I can, just take 2 to the power k minus 1 minus 1, because then one of the bits will not be set. Okay, so there shouldn't be any bit that is set in. Okay, so if you consider the bits here, like there are how many bits? If you have 2 to the power k minus 1, then you have k bits, right? So each bit can occur in at max n minus 1 positions. Okay, so each bit can occur in at max n minus 1 positions. So we can select n minus 1 from these n. Okay. Okay, great. But if I just select the bits here, each bit can go in any of the positions. Yeah, right. Now each bit must go in n minus 1 positions. That is the point. So it's like C n comma n minus 1. It's like k to the power c to c n minus 1. Something like this. K to the power c n comma n minus 1 is definitely n, right? Yeah. Okay, this seems to be different here. So it's like there are k bits and each bit has n minus 1 positions to decide where to come. Shouldn't this have been n comma k? Oh, right. Because that thing will be in the power, like k will be in the power because there are k bits, right? Yeah. So this seems fine. Okay, great. So two problems are done here. Moving on to problem C. Product 1 modulo n. Find the longest subsequence of 1, 2, so on up till n minus 1 whose product is 1 modulo n. P can be obtained from A by deleting. What do we need to find here? Given an integer n, find the longest subsequence of 1, 2, so on up till n minus 1 whose product is 1 modulo n. Please solve one. Sequence B is a sequence of an array. B can be obtained from A by deleting some. Okay. Given an integer n, find the longest subsequence of. Okay, we need to find a subsequence from this. Okay. Whose product is 1 modulo n. Okay. Okay. Let me think about this on pen and paper. Find the longest subsequence whose product is 1. So you can always include this 1 everywhere. All you need to do is find the other numbers. Okay. So let's say you decide to choose 3 here. Oh, okay. Okay, let me think about it. Okay, so first of all, the numbers that I have to select, they should have a GCD of 1 with n, right? Yeah. Then AX congruent to B mod M solutions. GCD of 8 and M. If D divides B, okay, then D should divide B, right? If I select a number, that is fine. Then I also need the numbers. Okay. Then I will need a number that is good. Has exactly D solutions. So that should have exactly one solution. AX. Okay. Then the GCD is still again 1. Right. The GCD is still 1. Then what do you do? Okay. Can I select all these numbers? Will they give me my answer? If I select all of them that are congruent to, sorry, that have a GCD of 1 with n. For 5, because we could have also selected 4 here, but we did not. Let's see this. That are co-prime with n. So are there some properties here? I think they've just given the code here. No special properties. Product of all numbers. Maybe I can try out the fourth problem till then. Okay, let's think for another 10 to 15 minutes. Oh, I guess there is a theorem for this, like the product of all the numbers that are co-prime to n. Hmm, is it actually true? Like if you consider 8 here, then you have 1, comma 3, comma 5, comma 7. Okay, fine. What if you have 6 here? Then you have 1, uh, 5. Oh, this is actually true. So you can just remove one of the numbers. Oh, this becomes really standard then. Okay, so if this is product equals to 1, then I just print all these numbers. Okay. Is not equal to 1, then what do? Then I remove the last one. PPP. Okay, this is great. This should have been t equals to 1. Okay, let's see. 1, 2, 3. Great. What about date? And what about 7? They should have. Okay, seems fine here. Yeah. Okay, so this is like a very cool problem. It is based on this theorem that I just read. That is that the product of integers that are relatively prime to n is congruent to plus minus 1 mod n. So here what you can do is like if it is already equal to 1, then you can print out all these numbers. Otherwise you can skip the last one because it will be congruent to minus 1, and removing that will, you know, result in the whole set of numbers being congruent to 1 mod n.